let's get started. Let's first recap what we learned last week. Last week we learned some of the basics of binary PAM, right? And there are two ways of doing binary PAM. One is antipodal signals, and second is orthogonal signals. And antipodal basically means that we have two symbols. Each one is called a symbol. So we have two symbols, but these two have opposite sign. Opposite sign. That's what they mean as antipodal. So one symbol called S1 has positive value, and the other S2 has a negative value. Those two have the same amplitude, but the sign, only the sign is positive and negative, right? That's what they mean as an antipodal signal. It's something like this. For example, if you see that this is a voltage, maybe 5 volt, minus 5 volt, something like that, right? So these are symbols. Eventually, this is a modulation. So before this modulation, for example, we have a PAM, binary PAM. So the input to the binary PAM is going to be 0 or 1. And the output of this binary PAM is this one or this one. For example, like this or this. If the input is 0, you get this output. If the input is 1, you get that output, right? But what we get as an input is a bit sequence, like a 0, 1, 1, 0, 1, something like this, right? We get a bit sequence, one after another. So therefore, you're going to get one of these every time. And this duration, in this case, it's a TB, right? This TB. That duration actually is the same as a bit duration. Our bit is this long, right? Each bit is this long. So that is a bit duration. But in this case, this is a one-to-one mapping. One bit mapped to one symbol. So therefore, bit duration, original bit duration is the same as symbol duration. This S1, right? Symbol duration in this case. So TB, in this case, actually, this is a bit duration, but this bit duration is the same as a symbol duration. That's the antipodal signal. And this plot is called the Constellation Plot. And later, we're going to look at the Constellation Plot many times. But right now, you can just remember that this is called the Constellation Plot. And what we can see from the Constellation Plot is the amplitude and phase, right? We can get those two informations, amplitude and phase. In this case, it is actually 1D, the one-dimensional plot, right? There's no Y. We only have X, so that's one-dimensional. So therefore, you cannot see the phase. But anyway, we'll look at that later. So that is antipodal. And second thing is orthogonal. In this orthogonal signal, this one is the same as on-off keying, on-off. So when you transmit this symbol, it's on. The second symbol means off. So it's like on-off signal. It's like on-off signaling, right? But other than that, everything else is the same. It's also like a 0 or 1. So the bit sequence again is 0, 1, 1, 0, 1, something like this. And when you get a 0, if this is orthogonal binary PAM, again the input is 0 or 1, and the output is like this. That's going to be your output, right? If there is a 0 input, you get that as output. 1 coming in, you get that coming out. Right? So that is the orthogonal signal. So simply the antipodal or orthogonal, that is a different mapping. Okay, what is the mapping? Bit to symbol. Okay, bit. These are bits. These are symbols. That's a mapping, bit to symbol mapping. Okay, so we are going to do different mapping depending on orthogonal or antipodal signals. And symbols is what we are transmitting to the channel. What is the channel we are using in this case? Remember that PAM kind of modulation is only used in chip-to-chip communication, right? This is not wireless. Okay, we are not transmitting this signal to the wireless. So the channel is like wire, for example, right? So through that wire, these symbols is going to the receiver. So this is what we transmit to the channel. Okay, so that is the signal through the channel. That is called a symbol. So remember what the definition of symbol is. Okay, symbol means you are transmitting symbol over the channel. Okay, this one is on the channel. Okay, let's move on. These are the some detailed communication system model, but we can simplify this whole picture into this one, right? So remember the difference between WT and NT. We have two different noise, right? Because we have a filter here at the receiver. So if we simplify this whole picture, then we can simply write it this way. So input the transmitted symbol ST, this is ST, goes into the channel, and inside the channel we are simply add noise. But this is not WT, this is simply just NT, right? Because this is just simplified model. What is actually happening is this one, but we can simplify this whole picture into this model. Okay? So from now on, we are always going to look at this model, simple model. Okay? We discussed some of the optimum receiver design last week. And one thing that we discussed was a correlation-based demodulation. What we are trying to do here is we receive symbol, RT, right? Here, RT. This RT is what we received. Let's go back here. Here's RT, here. Okay, we are starting from here. What is that RT? Here, this is RT. We basically, this model and this model is the same thing, right? This is just simplified model. So we are starting from here because we are going to talk about receiver now. So here's a RT. This RT is ST plus NT, right? Transmitted signal plus noise. That's our RT. That's our received symbol or received signal. And this received signal goes into demodulator, signal demodulator, and detector, and that's what we call as a receiver. Okay? The whole picture is a receiver. And the goal of this receiver is to detect 0 or 1, because eventually what we transmitted is a 0 or 1, right? So we need to make a decision either 0 or 1. So we need to recover 0 or 1. That's the goal. So what we are trying to look at is inside of the receiver. Let's look at the inside of the receiver. This receiver can be designed in two different ways. One is correlation-based demodulator, and the other is matched filter. And this picture shows you the correlation-based demodulator. So let's take a look at it here. We have RT. This picture right here, right? This picture is a detailed block diagram of this one. This picture and this picture is the same. Actually, this one, right? I'm talking about this one. The red one and this one is the same. This picture is a little bit more, this picture right here is a little bit more detail of red box. Okay? So inside the red box, we have these things. So we get RT as the input, right? That's what we see here. RT is the input. And we know that RT is ST plus NT. Okay? And we have signal, we have some signal called the psi. We have a psi 1 and psi 2. So let me draw it here. We have RT that goes in. So let's assume the antipodal signal, right? Which means that the transmitter transmit either this one or this one, right? So that's our transmitted signal. Maybe this one or this one. Right? Yeah. So let's go back to the transmitter for one second. Right here in the message, we are transmitting 0 or 1, right? So if we use a binary PAM with antipodal signal, what we're going to get here eventually is this one or this one, right? So that is our modulation, binary PAM modulation. So that is going to be ST. So ST is going to be either this one or this one. Okay, I'm talking about only one symbol. Of course, there are many of these symbols, right? One after another. But only looking at one symbol, ST is going to be this one or this one. So this ST is going to be this one or this one. So that is added with noise. So what does RT look like? So ST will look like one of these. So of course RT probably look like something like this or something like this, right? That's going to be RT. So that's what we receive here. Because we have a noise, so RT is affected by noise. So we receive that kind of signal in here. Okay? So we receive this kind of noisy signal coming into the receiver. And inside the receiver, we already know that transmitter use the antipodal signal. Because we, transmitter and receiver, both agreed. Okay, let's use the antipodal signal. Or let's use orthogonal signal. Okay, RSTX, they agreed. They agreed to use the same modulation. So receiver already knows that we need to use antipodal signal. So we prepare the answer. We prepare the correct answer. If this is 0, if 0 is transmitted, we need to receive this, right? If 1 is transmitted, we need to this. So since we already know the antipodal signal is used, the transmitter, we just prepare the perfect symbol here. Okay, we just prepare that. And then we multiply that perfect symbol here. Since we have two perfect symbols, but we don't know which one is the right one, right? So that's what we need to find out. So we're going to multiply into the receive symbol. That's what we have here, right? And next to the multiplication, we're going to do integration. Once you do this integration, what we're going to get here, what we're going to get right here is integration of this one and RT. That's what we are doing, right? That's what we are trying to do. Here, we're doing integration of this. So mathematically, this is what we are doing. This. That's what we are doing. But when you put this equation into the block diagram, this is a block diagram. Right? Integration of this one multiplication in this. So RT times psi 1t integration of those things. Right? So this is mathematics. This is simply equation. This is a block diagram. Now the question is, why do you want to do this? What is this? This one basically tells you the correlation between these two signals. That's why we are doing this integration. So the meaning of this integration is that we want to calculate the correlation between these two signals. This one also, right? We are trying to calculate the correlation between these two signals. Why do you calculate the correlation? Because we receive some kind of noisy signals, right? And we are trying to see if this one is close to this or this one is close to this. That's what we want to decide. So how much this one is close to this or how much close to this? That's why we are trying to calculate the correlation. If we have a high correlation between these two, let's say this signal looks almost the same. Okay, if the RT looks almost the same as this one, this is a perfect signal. If there's no noise, let's say there's no noise, then we're going to receive this or this, right? Because there's no noise. But since we have noise, we have a noisy signal, but still noisy signal looks almost like one of these. So we're trying to see how those two are close, okay? Looks close. So those, if these two looks almost similar, then we're going to get high correlation here. And we're going to get low correlation between these two. So we have a low value. Okay? So that's why we are calculating correlation. This is why we call this is a correlation-based demodulator. So we are basically calculating correlation here. And here, it is a correlation between RT and this one. This one is correlation between this one and this. Okay? But when you look at this integration, this is a continuous time calculation, right? So when you look at this one looks almost the same as convolution. When you look at the convolution, let me tell you one thing. When you do convolution of these things, right, and we have a TB of duration, you know that the answer is going to be like this, right? And we have a 2 TB here and TB here. So you have a maximum value at the time of TB. Same thing happens here in the integration. Okay, so exactly the same thing happens. So that's why when you do this calculation, this integration, and when you plot this integration actually gives you some this kind. I'm basically doing integration of these two, right? Put that here, and you're going to get some value like this. So you have a maximum value at TB. So therefore, what you need to do is that you need to do sampling. This is a continuous time, right? So you're going to get the continuous value, and the value changes like this. So what we need to do is we have to do sampling at t equal to TB. Okay, this is the point that we sample. Why? Because at that point we have a maximum value. Same thing happens here. Here, exactly the same thing happens, right? You're going to get the right value at the same position. In this case, when you look at the correlation, let's look at the correlation between this and this. Think about that you are doing convolution between this and this. What do you get? Maybe you get something like this. Maybe something like this, right? So correlation between these two is pretty low. So you get some value when you sample at TB. So that's why we do sampling here at t equal to TB. This means the sampling. t equal to tb at the same point, same time. This means sampling. After you do sampling, right, then you're going to get this value right here. So for example, positive 0.8. You're going to get this value right here. For example, negative 0.2, something like this, right? You're going to get some value after sampling. That's what is happening inside this demodulator. So we are looking at this, right? So that's the internal structure of signal demodulator. So once inside this signal demodulator gives you this value, these two values, so now these two values will go into the detector. So what do you need to do in the detector? Detector is going to make a simple decision. And it's very clear how to make a decision, right? So what is going to be the decision rule? The rule is just pick the biggest one. That's the decision. In this case, just to think about the amplitude only, because you don't care about the sign. You get a different sign because the original perfect answer has a negative and positive. So sign doesn't matter. Look at only the amplitude. In this case, this one has a larger amplitude than this one. So the decision is this one. Okay? We just simply decide that, oh, this one probably is transmitted. So what does that mean? Eventually, the input to the detector, let's look at the detector. Input to the detector is going to be these two values. What's going to be the output of the detector? Eventually, the output is going to be 0 or 1. That's your final answer, right? So your input to the detector is these two. So when you look at these two inside the detector, again, the rule is just pick the biggest one, the larger one, right? In this case, in this example, you're going to pick this one. So once you pick this one, what is the output? 0. Because I mapped 0, I was using this mapping, right? At the transmitter, when I have a 0, I mapped into this. When I have a 1, I was doing a mapping into this, right? So that is a mapping. So at the receiver, you're going to do the same mapping. Let's say you get this one is the output. I'm saying this one has a larger value. Then it's for sure that this one is transmitted. If this one is transmitted, what that means is original information is 0. So that's how you decide inside the detector. So now my decision is going to be 0 in that case. Yeah, simple like that. But that's what we call as optimum receiver. That's the perfect, that's the optimum way of making decision. Okay? So what is important in this picture is signal demodulator. Detector is pretty simple, right? We're going to get two values, just compare. Inside detector, we have a comparator. Comparator is a hardware block to compare two values, right? So we basically compare two values, like these two, for example. Just compare these two values and pick the larger one. Okay? And just use the original mapping between 0 and 1. That's all it does. Inside the demodulator, we need to do these calculation. But what is the calculation you need to do? Correlation. We have a two correlator. This is called a correlator. Right? Correlator. This is correlator. So we need to have two correlators. And these two correlators have to run in parallel. You need to calculate the correlation using these two correlators in parallel. We're going to get, and after that we do sampling at the right point, the middle point, and you get these values. Okay, so that's the optimum receiver. So that's a block diagram picture. when you look at the same thing, this whole picture, this whole process in equation, these are the equation. Okay, this is simply mathematics. We have a RT, this is RT. We just changed the variable to tau, but this is RT. This is what we received. Okay, and psi is our perfect signal. This one or this one, that's psi. And what we are trying to do is that in one correlator, we have two correlators, right? Two correlators. But each correlator, we are doing this calculation. We receive RT, calculating correlation with phi1. You can think about this is 1. And we have another correlator for 2. Okay, this is the calculation for one correlator. Same thing happens again into the second correlator, right? So we're just simply doing correlation between these two. That's what we did here, right? But RT actually is same as ST plus NT. So mathematically, we just put this one inside instead of RT. So ST plus NT, something like that, right? And ST and VT, this one and this one is actually same. Why? Because this RT actually equals to this plus this, right? ST plus NT, right? That's how you get noisy signal. So that's how you do it. Just separate these two. Original ST and noise NT. Just separate them and put that in here. And after, so this is the, after that you get this one and sample it right here. And this is what we get after you get sampling at the TB. And you're going to get this. So that's simply a mathematical point of view. One thing that we need to remember right here is that I just give you an example, okay, just to help you understand. But this value actually, 0.8, is random. Okay? I'm just giving you one example, right? This value, let's call this value, and here this value as S1 plus N, S2 plus N. We want to call it that way. So what is S1 in this case? S1 is the value of this. Or this. The same thing. This one and this one same. So this value right here, that's going to be our S1. So example is like this. When you do mapping at the transmitter, so 0 or 1, that's bits. So this 0 is mapped to this one. But what is the level? Is this 1 volt or 2 volt, 5 volts? What is it? And 1 is mapped to this, right? But is this minus 1 volt or minus 2, minus 5? What is it? That's S1. You can use 2 volts, 5 volts, doesn't matter. Okay? You just pick your own, but that's going to be S1. And this level here is S2. Okay? We are going to use the same signal here at the receiver, right? We're going to use the same thing. So if you use 2 volts here, we're going to use the same 2 volts here. Eventually, we go all the same process. Then the output value we're going to get is perfect answer plus noise. Same thing here, right? S2 plus N. That's what you're going to receive here or here. Okay, positive 0.8 is just an example. Okay, just example that I gave you. What is actually received here is going to be original perfect S1 plus N. Let's say if there's no noise. Forget the noise. If there's no noise, then in this picture, we have no noise. So we're going to receive this, right? This is RT. So that RT comes in, and we have a same picture here, that goes in here, then you're going to get this perfect S1, right? Yeah, right. So we're going to get the perfect S1 right here. If there's a no noise. If there's a no noise, then we're going to get S1. Same S1. But because we have a noise, we are not going to get perfect S1. We're going to get S1 plus noise. So here, the value is going to be a random variable. S1 is a constant because once you decide S1 is plus 1, then it's always plus 1. That's a constant. Okay? If this is, let's say, plus 1, if S2 is minus 1, then we have plus 1, minus 1. All of that, again, we have a plus 1 and minus 1. It's going to be constant. Once you decide, it's constant for the whole system. It never changes. The reason that we have some random value here is because of the noise. Right? Because of the noise. So because of the noise, sometimes you're going to get 0.8, sometimes 1.2, something like this, right? So what we're going to look at is what is the distribution of this value? That's what we're going to look at. So what is the distribution of this S1 plus n? If there's no noise, and if we only have S1, then S1 equals to plus 1. So we always get S1. We always. Let's say we transmit million samples, million bits. All of those million is going to be S1 or S2. So we are going to get S1 or S2. If there's no noise, let's say there's no noise. If there's a no noise, this is what you're going to get. Maybe 500,000 here, 500,000 here. So total million. That's what you're going to get. But we have a noise, right? So therefore, you are not going to get plus 1 all the time. Sometimes you get 1.2 or 0.8 or even 0.5 or even 0 sometimes. Okay, sometimes, right? Let's say you transmit plus 1, but the noise is very big, negative. Then sometimes you get 0. That's possible, right? Or sometimes very high value, like 2. So all of these, you're going to get random over those million samples. You're going to get this distribution when you transmit S1. Same thing happens when you transmit S2. You never get always minus 1. Sometimes minus 2, sometimes minus 0.2, something like this, right? You're not going to get minus 1 all the time. So therefore, you're going to get this kind of distribution when you transmit S2. So when you transmit S1, you have this distribution. When you transmit S1, you have this distribution. But what this distribution look like? That is a Gaussian distribution. Why? Because we have Gaussian noise. This is Gaussian noise, right? The amplitude is Gaussian. So when you look at here, right? Let's look at the S1 plus n. We learned the random variable, right? In this case, S1 is constant value. N is Gaussian random variable. Let's say S1 is 1, plus 1. Okay? And N is random variable, and it's Gaussian. Let's call it this way. This means normal, right? Normal means Gaussian, right? So Gaussian, you know the Gaussian distribution has 2 parameters, mean and variance. And mean is 0. This is called the zero mean Gaussian. and variance is sigma square. Okay, that's the random variable. That's the statistics of our noise. Our noise n has this statistics. The average is always 0. Average is 0. And sometimes goes up, positive, negative, positive, negative. But when you average it out, that's going to be 0. The mean is 0, right? But we have a variance going up and down, up and down. We have a variance, how much we vary. That's a sigma square. That's our noise. That's the statistics of our noise. But this noise random variable plus constant value, plus 1. In that case, this whole picture, this whole thing has what distribution? The distribution of the whole thing is going to be, again, the normal, random, the Gaussian. Only the mean is changed, right? Because you are just simply adding constant. This random variable is, original this random variable n looks like this. We have a mean 0 and sigma square as a variance. But now what we're going to do is that we are adding constant 1. Like this, right? We are adding constant. Let me just change it. We are just adding a constant, S1. This S1 is a constant value. So what we're going to happen is this whole distribution is now shifted. And the middle point is now becomes S1, right? That's it. That's it. Simply. It's a shifted. So it's not non-zero Gaussian. It's a Gaussian with the mean at S1. The mean is at S1. You can do the same thing for S2. In that case, this Gaussian noise distribution, the zero mean Gaussian, will be shifted into here. So now the mean is at S2. So that's why we have these two Gaussian distribution. One has the mean of S1. Second one has the mean of S2. So this one is the random. This one is the Gaussian distribution with the mean S2 and sigma square. This one is again another noise, another Gaussian random variable at mean S1. That's it. Okay, so that's why we have a two distribution like this. Please remember this picture. This is very important picture. We're going to look at this picture many, many times later. Okay, tomorrow and the next week and the following week, we're going to look at this picture many times. Okay, just remember this picture. We have two Gaussian distributions, and each one has a different mean. This distribution, this Gaussian distribution has the mean at S1. This one has the mean at S2. And why is it S1 and S2? Because of all this, right? Just simply this is our S1 is what we want to get. But that S1 plus noise, and noise has a distribution because noise is random. S1 is a constant. Maybe it's a +1 or -1 or +2, whatever you decide, that's going to be constant. So that's why we have these two Gaussian distribution in binary case. We are talking about binary case. So we have only two symbols, S1 and S2, right? So that is the distribution when you have a noise. So when you look at only one distribution, that looks like this. This is the case when we have only one distribution. So the mean is at S1, right? Okay, let's move on here. So let's look at this picture. This is the picture that I just drew here. So we have two Gaussian distributions, and the mean for each distribution is going to be S1 and S2. But the left picture and the right picture, the difference is that the left one used the antipodal signal, and right one is orthogonal signal. Now remember the difference between antipodal and orthogonal. Antipodal was S1 looks like this. S2 look like this. That's the antipodal. Whereas orthogonal signal looks like S1 is on, S2 nothing. Right? So therefore, when you look at these two Gaussian, it looks like this picture and this picture looks almost the same, right? Looks almost the same. The only difference is that actual S1 and S2 value is different. Here is S2, here is S1, but S2 is minus some value, S1 is plus some value. However, in orthogonal, we still have S1 and S2, but S1 has some positive some value, S2 is 0. Why? Because S2 is 0. S1 is some positive value. So that's only difference. Everything else is pretty much the same. Okay? We have a two Gaussian, but actual value here, S1, S2, S1, S2, those value is different. But there's one more difference here, right? One more difference. Here's one more difference in this picture. When you look at the value here, right, in antipodal signal, this value is going to be plus root square EB. This value is minus root square EB, right? So what does that mean, root square EB? EB means bit energy. Okay, energy of bit. Each bit has a certain energy, right? Each bit. So that's EB. We just call this one as EB. So each bit has a certain amount of energy. That's what we call as EB. Then why do we put the root square? Energy is the same as, energy is kind of power, right? But this one is not energy. Energy cannot have negative, right? You can never have a negative energy or negative power. Energy is just energy, always positive value. But this S1 and S2 is what you transmit. This is a signal that you transmit over the air. This is a symbol, right? You're transmitting this symbol or that symbol over the channel. That's not energy. This is not energy, right? This is actual symbol. So that is amplitude. So what's the relationship between amplitude and energy? Energy is always square of amplitude, right? So energy is a square of amplitude. So therefore, if we call that the energy of bit as EB, what is going to be the amplitude? Root square of the energy is going to be amplitude. Okay, so this is energy. Okay, remember this is energy. See, E means energy, energy of bit. But this actual symbol is the amplitude. So that's why we put the root square of the energy. But this is the antipodal, so we have positive amplitude and negative amplitude. But remember that whenever you see the E sub B, that means bit energy. This is bit energy. Let's go all the way back here. Let's look at this picture. This is the case of antipodal, right? So whenever we have a 0 or 1, we transmit positive, negative, negative, positive, things like that, right? So let's calculate the energy here. What you need to do is you have to do square, right? You have to square because this is each one is amplitude. So you're going to square. This level here actually is root square EB divided by root square TB. That's level. So let's square. And how do you get the energy? We just calculate the energy inside the bit. So what do you need to do? That's how you calculate the energy. Okay? Simply you do square. Because why do you square? Because this is amplitude. So we're going to square, right? And then just simply integrate during this bit duration. Then you're going to get bit energy, right? This is going to be EB. Okay? So TB cancels. So we're going to get EB. So that's EB is going to be your bit energy. What about this second symbol? Second symbol is a minus amplitude. So you get a minus here. But still you're going to get the same energy, right? Because anyway, negative value square becomes positive. You're going to get the same energy. So in this antipodal signal, what happens is every bit have the same energy. Negative, positive, positive, negative doesn't matter. Every bit has the same energy EB. That's why we have this level. Okay? Remember why we have this root square divided by root square TB? That's because that the bit duration is TB. So we are gonna. This is how to calculate the energy in the bit. Okay? So that is the case of antipodal signal. What about orthogonal? Let's go to the orthogonal. In orthogonal signals, how do you calculate the energy? Same way. Let's calculate the energy for the first one, first symbol. You're going to do the same calculation. In this case, as you can see, the level is a little bit different, right? We have a 2 here. That's what I'm trying to tell you. Let's see that we have this one, and we square and calculate this, right? What do you get? It's going to be 2 EB. Oh, we have a 2 times of EB here. Something is wrong, right? Because what I want to do is average bit energy should be EB, but in this case it's 2 TB. What's wrong? Nothing is wrong. Because next symbol, bit energy is 0. In this case, the bit energy is 0, right? So therefore, the first symbol here, you have to have E sub B. That way, when you take an average over the whole time, the average bit energy should be EB, E sub B. So this is why we have root square 2 here. Okay? In on-off keying, when you transmit nothing like this, there's no energy, right? There's no energy. So therefore, when you transmit something, you have to have 2 times of energy. That way, average out, it becomes EB as the average energy, average bit energy. Does it make sense? So that is why we have root square here, root square 2. EB divided by root TB. This is why we have a 2 here, right? So put that all together. Now this is the case. Going to the okay, so going to here. So this is a case of antipodal signals. In antipodal signals, we are transmitting this symbol or that symbol. This symbol has this amplitude. That symbol has that amplitude. Well, if you, okay, maybe you can introduce the time domain TB, then, okay, let me put it this way. So this is the level. Okay, that's what we saw in the previous slide, right? This is the level of symbol in the antipodal signals. However, in the orthogonal signals, this level should be 2 times of EB divided by TB, positive. In this case, the level is 0. Right? So why do we put it this way? The reason is we want to make bit energy to be always E sub B. Average bit energy. In antipodal signal, the average bit energy is EB. Orthogonal signal, again, average bit energy is E sub B. That's what we want to do. So that's why we have root square 2, and that's why we have these two Gaussian pictures. Okay. So next slide here simply tells you how to work in an animation, kind of, right? But this is what I just discussed. So here, this is the antipodal signal. We have this kind of noisy signal coming in. This is RT. So this is a noise signal. That's what I have here, right? It's a noisy signal. But we already prepared the perfect signal, and we are trying to do correlation, right? So how to calculate correlation is like, this is a correlation equation. And how to do correlation is, see here? This is like a convolution, like this, right? Sliding, like this. And look at the output here. When you slide, this is RT, and this is my perfect signal. So when you do like, when you calculate correlation, you are basically sliding. One is a sliding, right? When you get sliding, this is the output of the correlation. Let's see here. In this case, we have no overlap. No overlap, so correlation is 0. When you have a slide little bit, so we have a little bit of correlation, little bit of overlap. We have a little bit of correlation here, right? The value goes up. Again, keep moving to the right. Again, this one goes up. Again, keep moving. It goes up. And you see that now this one and this one has like a matched in time, right? Synchronized in time. So that's the case we have a maximum overlap. And that's the case we have a maximum value, right? When is that time? That's the time we have a TB. TB is the time that we have a maximum overlap, like this, right? So that's how to visualize what's happening inside the correlator. And keep going. Actually, keep going. Then this one keep moving, right? Now the overlap is getting reduced. So therefore, it's coming down. Okay, it's going down as time goes. So here is the point we always have a maximum value. So that's where we sample it. So once we sample it, then what we're doing? Once you sample it, then you're going to keep that value. Because that's where we sample it, right? Once you sample it, and you're going to get value, like a plus 0.8, right? You're going to get this value. Then you just keep it. Keep it. Same way. Same for the second correlator. We have two correlator, right? One correlator here, second correlator here. Same thing. For the second correlator, we have a negative signal here as a perfect signal. So it goes down like this. And then here is the minimum value you're going to get. And we sample it at that point, and we keep it. Keep that value. This picture shows you the case where we have no noise. If there's no noise, that's what's going to happen. But if there is noise, then we're going to get different value, right? Maybe something like this or something like this when you have a noise. Okay? This is a case when we have a no noise. Okay, that's the correlation-based demodulator. Now the second thing is a matched filter. Okay? Matched filter is a second way of designing an optimum receiver. Okay, and this matched filter, you'll see this matched filter in many different communication systems. But Okay, let's do this tomorrow. Okay, so let's stop here today.